Let's start from the Lagrangian density with a complex scalar field L equal to del mu psi star del mu psi minus m squared psi star psi. We know that from this equation we can derive the Klein-Gordon equation del mu psi plus m squared psi equal to 0. So this is what you can obtain from the field equation del mu del L d mu psi star equal to d L with respect to psi star. This derivative here is equal to d mu psi, whereas this derivative here is equal to minus m squared psi. So all in all, what you get is that equation there. Now we want to generalize this kind of theory for a scalar field to a theory where we have a vector field, a vector of complex scalars. So we will consider psi to be given by psi1, psi2, and so on. So this will be a vector where each of these will be a scalar, and these scalars will have to satisfy the Klein-Gordon equation there. Now, we want to consider something which is invariant. We want to construct a Lagrangian which is invariant, and we are going to do very simple considerations without resorting to Lorentz transformations. In particular, first we start from considering something like this: psi dagger psi. So it's easy to understand that this will be a scalar. So for example, if we take the transpose of this and also the complex conjugate, so we take the dagger, we will get exactly the same thing, psi dagger psi. So it's very straightforward. But if we take only the complex conjugate, for example, of this, you get the same thing, because this means that we are going to consider psi 1 star psi 1 plus psi star 2 psi 2 plus dot dot dot. And when you take the complex conjugate of this, you are going to get the same thing, because this psi 1 can also be put here. Now we are treating scalars in here, so this psi 1 will be a complex scalar, and so will this one. But when I write psi, actually I'm thinking of this as a column vector, whereas this psi dagger will be a row vector. So this is like a dot product. You can think of this as a dot product. And then, in principle, we can also consider terms of this kind, del mu psi dagger del mu psi, where this psi here will be a column vector, whereas psi dagger will be a row vector. And considering basically what we did here, if you take the dagger of this, well, you get del mu psi dagger del mu psi, and you can lower and raise these indices by using the metric tensor. So you can easily understand that this will also be equal to del mu psi dagger del mu psi. So in principle, something like this can appear in a Lagrangian. But what we are going to do is we are going to consider a term which is only linear in the derivative terms, not quadratic. So we can think of this as a quadratic term, because we have del mu multiplied by something which contains this del mu, right? So you can think of this as something quadratic, let's say quote-unquote quadratic in del mu. But we want to consider something which is linear. So we're going to take psi dagger, because we need to get a scalar. Remember, we need to get a number, a real number. So when we act with a row vector, we also need to have a column vector here. So we have del mu psi here, but we need something else. So this derivative appears only one time, but we also need something else, and in particular something which contains the index mu, and in particular in the upper position. And let's also multiply by the imaginary unit I. So let's try to find out something about this object. And as I said, we need this term a mu, and we need to understand something more about this. In general, a mu here will be a square matrix, because this square matrix can act on a column vector, and this will give you another column vector with the same number of components, and then when we act with a row vector with the same number of components, we get a number, right? And now let's consider the dagger of this. Let's consider the dagger of this. We want this to be basically the same. So if we take the dagger of this, we want it to remain exactly the same. Let's see if this happens. Remember that this term will be contained in a Lagrangian. So we have minus I, which comes from the complex conjugate of I. Then we get del mu psi dagger, a mu dagger psi, like this. We can rewrite that in this form: d mu minus I psi dagger, a mu dagger psi, plus psi dagger, a mu dagger I d mu psi. Now this term, to which we apply this derivative, will be the Dirac current. The first divergence of the Dirac current is equal to 0. It is something that we impose, and it can also be derived from the Dirac equation. Will vanish, and it will not be contained, or let's say it will not affect the field equations. Only this term here is actually important. So we need to make sure that this term is coincident with this one. If we want a number that's a real scalar, so we have to make sure that basically a mu dagger is equal to a mu. So this is what we can impose: a mu equal to a mu dagger. And now we can define a mu as a product of two matrices. In particular, I will call these matrices gamma 0 and gamma mu, where, well, the index mu can go from 0 to 3. And this gamma 0 is already contained in one of these gammas here, gamma mu. When mu takes the value 0, you get gamma 0 squared here. But now, from this, we have to impose that gamma mu dagger, gamma 0 dagger is equal to gamma 0 gamma mu. Now, if we choose gamma 0 such that gamma 0 is equal to gamma 0 dagger, which is equal to gamma 0 inverse, gamma 0 to the minus 1, this means that gamma 0 squared is also equal to the identity, and we can also write gamma mu dagger equal to gamma 0 gamma mu gamma 0 from here and from here, basically. And so this is a property that these gamma matrices need to satisfy. Then remember that we considered psi dagger a mu I del mu psi. Now we defined a mu like this, so we can also write this as psi dagger gamma 0 gamma mu I del mu psi, and this can also be written by definition as psi bar. So we define psi bar to be psi dagger gamma 0, like this. And let's also check that psi bar psi is invariant if we just take the dagger of this. So if we take the dagger, we get psi dagger, psi bar dagger, but this is psi dagger. psi dagger gamma 0 dagger, which is psi dagger gamma 0 dagger, which is gamma 0 psi. But psi dagger gamma 0 is none other than psi bar. So we see that indeed psi dagger psi is invariant with respect to this dagger operator. And also we proved that the same holds for this. So psi bar I gamma mu del mu psi, basically. Let's consider the following Lagrangian, which is made up of those two invariant quantities. And when I say invariant in this case, I mean with respect to the dagger operator. One can also dig deeper and find out that this invariance has to do with the Lorentz transformations. But we are doing very simple considerations here. So we have psi bar gamma mu I del mu psi, and then we put a minus the mass of the particle that we are considering. So this will be an invariant quantity, which is the mass, and we have psi bar psi. Now, from this one can derive the field equation, for example, for psi, and something similar for psi bar. So you can derive two field equations, one for psi and one for psi bar. Well, if you vary this Lagrangian, and in particular if you vary the action with respect to psi bar, you get the equation for psi. So you get gamma mu I del mu psi minus m psi equal to 0. And now we want to impose other conditions. And these conditions will give us more information on these matrices gamma mu. This is also known, by the way, as the Dirac equation. But now we want to impose that this psi, which you can think of as a column vector, in particular the components of psi, will satisfy the complex scalar equation. So in particular the Klein-Gordon equation. So we want the scalars which compose this vector psi to satisfy the Klein-Gordon equation. And in particular they have to satisfy del mu plus m squared, and then here we have the components of psi equal to 0, like this. So let me rewrite the Dirac equation like this. I will put an equal sign here, and I will erase this part like this. And now let me act on both sides of this equation with gamma nu I del nu. So here I have gamma mu I del mu psi, and then here I have m gamma nu I del nu psi. But now it's easy to see that this part here will be equal to m psi, because remember that psi should satisfy this equation here. So this is just equal to m squared psi, like this. Whereas this part on the right is equal to minus from I squared, and then you get gamma nu d mu psi. But now you see that, I mean, this derivative operator, this is a second derivative, if you think about it, well, this is symmetric with respect to the indices nu and mu, so you can also write it as d mu del nu, according to the Schwarz theorem, and the Schwarz identity. So if you change the order of the derivatives, you will get the same thing, assuming that there are some nice properties of this function psi. And now I'm going to rewrite minus gamma nu gamma mu del mu psi like this, minus 1/2, and then I'm going to write it as the anti-commutator between gamma mu and gamma nu, and then I have del nu psi, And this can be done due to the symmetry of this part of the expression. So remember that this is just gamma nu plus gamma nu gamma mu. So this is a simple property. And this should be equal to m squared psi. Now remember that we have to impose now that this will have to give us the equation del mu psi plus m squared psi. So basically we have to impose that this is equal to minus era mu nu, right? Because if we impose this, then we get exactly this equation. So here I have to set it equal to 0, and we get this equation here. Therefore, another important property that the gamma matrices should satisfy is this: gamma nu anti-commutator equal to 2 era mu nu, which is a well-known property of the Dirac matrices